Welcome to the Depth Dive. Today, we are wrestling with a really alarming strategic problem. It's something that's defining the entire contemporary military landscape.
It really is. We're talking about this jarring economic and technological asymmetry that's, well, it's forcing Western nations into some, frankly, unsustainable choices.
Exactly. And so for this deep dive, we are digging into a concept that proposes a really radical pivot, a shift in mindset that moves us away from, this constant pursuit of exquisite gold-plated perfection.
And towards what? Towards the acceptance of sheer disposability and volume. It sounds counterintuitive, but it's essential.
It does. And for the last, 2 decades, Western doctrine has really perfected what this white paper calls the golden arrow.
Right. The low volume, high precision, and, at the end of the day, exorbitant cost platform. Our entire military strategy was built on this idea that our tech superiority justified any cost.
But while we were building these, incredibly advanced, beautiful systems, the adversary did something much simpler.
They just looked at the global commercial market. They embraced the swarm.
And the proof of this sort of strategic failure, is immediate. And honestly, it's painful. We've defined the problem as the economic inversion.
And it all rests on this one single brutal fact.
A high-end, $2 million air defense interceptor missile, built over decades, maintained by these incredibly complex logistics chains,
Is being routinely expended to do what?
can neutralize a $500 commercial drone you could buy online.
It's fiscally bankrupting.
Yeah.
There's no other word for it. When you look at the economics of a long, high-intensity conflict, if your enemy can force you to spend 4,000 times the value of their asset just to stop one little strike,
They're waning.
they are winning a war of attrition long before the first major land battle is even fought. They're using fiscal pressure as a strategic weapon. This is the asymmetry we absolutely have to fix. And fast.
So the mission of this deep dive, then, is to unpack the proposed solution. It's called the Military Internet of Things, or MIoT.
And the core proposal is, it's genuinely revolutionary. It says we have to stop treating our sensors, our intelligence tools, our situational awareness assets.
We have to start treating them like capital assets, like they're valuable machinery or expensive jewelry.
Exactly. And start treating them as digital ammunition.
The goal here isn't just tactical, it's economic. It's about restoring what the paper calls fiscal ballistics.
That's the key phrase. We have to ensure that the cost of sensing, of verifying, and then neutralizing an enemy target is fundamentally and reliably cheaper than the target itself.
And the only way to get that cost advantage is through volume, disposability, and just embracing the sheer speed of commercial tech development.
There's no other way.
Exactly.
Yeah.
So over the next 30 to 40 minutes, we're going to unpack let's be honest, the historical and bureaucratic acquisition cycles that got us into this gold-plated mess in the first place.
We'll detail the 3 tiers of this new disposable hardware they propose. Everything from smart dust that's designed to biodegrade all the way up to these intelligent gateways.
And here's where it gets, I think, really interesting.
Mm.
We're going to talk about the surprising and frankly sophisticated way that commercial smartphone security protocols...
Things that are in your pocket right now.
Yes, like the hardware for your phone's fingerprint sensor are being deployed on the battlefield to make all this cheap equipment absolutely secure and tamper-proof. All right, let's start with how we got here. Because this isn't a new problem, it's deeply rooted in institutional history, in logistics.
Right. The post-Cold War assumption was that technological overmatch was worth any price tag.
Yeah.
The logic, for a while it was sound. If your jet or your tank was just exponentially better than the adversaries, a higher price seemed justified.
But that logic has been completely inverted.
It has, because of the democratization of technology.
Right.
The guts of advanced warfighting GPS chips, high-density batteries, advanced processors, they're all globally standardized now. They are cheap. And they're produced at a massive commercial scale that no defense contractor can ever hope to match.
So we're trapped in what the white paper calls the gold-plated cycle, specifically the sustainment trap.
And this trap has a massive, an often absurd timeline problem that is just baked into the bureaucracy.
When the U.S. Army or our NATO allies set requirements for a new major system, they're often trying to predict the future. They're projecting needs 20 years before the system even enters production.
20 years. Just think about the speed of technology. 20 years ago, the first iPhone hadn't even been released. We were all still using flip phones.
So that time frame is, I mean, it's just debilitating.
Completely. By the time that system is finally fielded, it's not just failing to meet that original 20-year-old intent.
It's already a huge logistical and doctrinal burden from day one.
It is the definition of fighting the last war, but with systems that were designed for the war before that.
The source material, it specifically references the infamous development of the Bradley fighting vehicle.
Oh, yes. The Pentagon Wars.
Yeah.
A perfect example.
It's the prime example of this failure mode, a simple, manageable requirement. You know, we need a scout vehicle. It enters the system.
And what comes out the other end, 40 years later, because that is the sustainment horizon we're talking about, is an exorbitant, confused, and heavily compromised platform.
The initial simplicity just gets lost in decades of required modifications and institutional, compromise.
And that systemic issue, the absurd time frame we impose on ourselves, is best captured by this one analogy they use, the Walkman analogy. It really grounds how absurd this is.
You're creating a cradle-to-grave life cycle for these proprietary military radios and sensors that spans 4 decades.
40 years. That single time frame, that sustainment window, it exceeds the entire commercial market lifespan of the Sony Walkman.
Which was a genuinely revolutionary, culture-shifting device when it came out.
Absolutely. It changed how we experience music, how we live our lives in public.
Which leads to the crucial and I think really provocative question that the authors pose.
If you are not confident that the sensor or the radio or the vehicle you're buying is as genuinely revolutionary and culture-shifting as the Sony Walkman was,
if you don't think it's going to change the world,
and why on earth are you building a logistics architecture that forces you to maintain and sustain it for 40 years?
And it's that mandatory lifespan that drives up the cost, right? It necessitates the extreme over-engineering.
It's the direct cause. We require nuclear hardening, exotic proprietary waveforms that cost hundreds of millions to develop, extensive physical shielding for everything.
Yeah.
All of this drives the initial cost of a single, highly specialized proprietary sensor up to $50,000.
Before it even leaves the factory.
Before it even sees the light of day. And once it gets to the field, the problem just compounds massively. This leads directly to the immense logistics burden.
Because these systems are classified as major end items, Class 7 assets, that's not just a label, it comes with a massive, heavy logistics tail.
It means specialized maintainers who need years of training. It means climate-controlled storage facilities, complex, bespoke supply chains for spare parts that only one factory, maybe in one state, in the entire world produces.
This overhead, then, it creates a really toxic administrative environment.
It does. It's what we call the command supply discipline program culture. Commanders, they understand implicitly that losing or damaging a $50,000 asset.
Especially if it's one of a very limited supply.
It could be a career-ending event. It generates a huge amount of professional anxiety.
So what's the natural human response to that kind of anxiety?
Preservation, not deployment. You keep those systems locked away in the container. They're perfectly accounted for, they're climate-controlled, and they're completely unused.
They only come out for the annual inventory.
Exactly. You bring them out for the annual inspection to make sure they look perfect on paper. So the result, perversely, is that these assets are perfectly preserved, they're logistically pristine, and they are utterly useless on an actual dynamic battlefield.
We paid a premium for gold-plated situational awareness.
And the institutional fear of losing the gold plate prevents us from ever actually gaining that awareness.
But how do you change that culture? It's not just the cost of the sensor. It's decades of institutional inertia that's screaming, don't break the expensive thing.
You have to change the asset classification itself. That's the only way. If a sensor is treated legally and logistically, not as a major end item, but as ammunition, as a consumable item, the anxiety just evaporates.
Right.
If it costs $100 and you deploy 100 of them, the failure of one isn't a career event. It's just operational waste, like a spent casing. The MIoT philosophy fundamentally redefines the asset to get rid of this command discipline burden.
That makes perfect sense. And you couple that logistics burden with the final critical problem, the obsolescence gap.
This is where we contrast the military block upgrade cycle, which is slow, it's measured in years, often delayed by funding, with the relentless agility of the commercial sector.
Moore's Law.
Moore's Law is the absolute enemy of the block upgrade cycle. Processing power doubles every 12 to 18 months. It delivers exponential performance gains and, at the same time, cost reduction. Software updates are pushed over the air rapidly at minimal cost. The commercial world has mastered speed and volume.
And the military is stuck fighting with outdated gear.
Precisely. By the time the military fields a Block 2 sensor that was conceived a decade ago, the commercial market has blown through 5 generations of chips. They're using a processor that's 10 times faster and a tenth of the price. The military system is functionally obsolete the day it arrives.
So we're fighting with museum-grade electronics.
Against adversaries who are leveraging the latest consumer-grade agility, which they can deploy immediately and at scale. The entire MIoT approach is designed specifically to dismantle this institutional inertia and finally adopt commercial speed.
Okay, so let's unpack the core tenets of the MIoT solution itself, because this is the real pivot point. If speed and cost are the problem, the solution has to be volume, disposability, and commercial standards.
Right. We're moving away from protecting a few highly protected, high-value assets to deploying a massive, ubiquitous sensing skin over the entire battle space.
A skin that is, by its very design, too cheap and too numerous to jam effectively.
And certainly too cheap to destroy profitably. It forces the enemy into a terrible economic choice. Expend your expensive, limited air defenses against assets that cost us almost nothing to replace. It flips that cost exchange ratio on its head instantly.
And the sources detail this shift by defining 3 specific tiers of hardware. They call them, collectively, digital ammunition. Let's start with Tier 1.
Tier 1 is smart dust, or as they call them, the expendables.
And we're talking truly tiny here.
Oh yeah. Coin-sized devices. They're designed for maximum velocity and disposability. They can be sown by drone swarms, dropped from high altitude, or scattered via specialized artillery shells across vast areas.
And what's the function? What makes them disposable?
Their function is extremely minimal. It's binary sensing, movement, yes or no, acoustic signature, yes or no. They are not doing any complex processing on board.
And the cost.
The critical cost target is less than $10 per unit. This ridiculously low cost allows us to treat them exactly like ammunition. You just don't care if you lose them.
So they're fire and forget.
Completely. They're powered by tiny little batteries designed for a very short operational life, maybe 48 to 72 hours, and they're engineered specifically to biodegrade quickly or just be left behind like a spent shell casing once their job is done.
Okay, so moving up the capability chain, we get to Tier 2. The tactical pucks, the workhorses of this network.
These are about the size of a soda can. They're robust enough to be emplaced by hand by infantry or dropped by light uncrewed aerial systems, UAS.
And these have significantly more processing power.
Much more. And more complexity than the smart dust. They're multimodal sensors, which means they're pulling in high-fidelity acoustic data and seismic data at the same time.
And this is where that onboard processing capability starts to become critical, right? They aren't just sending raw noise back up the chain.
Absolutely not. That would defeat the purpose. Tier 2 pucks run embedded, basic machine learning algorithms that are designed specifically for pattern recognition right at the edge.
So what does that look like?
For instance, they can distinguish the heavy, continuous vibration pattern of a tracked vehicle from the sort of oscillating pattern of a wheeled vehicle. They pre-filter the data to get rid of common false positives, like wind or small animal traffic, so they're delivering much cleaner data to the next tier.
And the cost target for these is still pretty low.
Still highly consumable, less than $100 per unit.
And consolidating all that distributed intelligence, that's the job of Tier 3, the intelligent nodes.
These are the brick-sized hubs. They are the only non-expendable assets in this whole mesh. Their primary function is data aggregation and routing.
So they're the brains of the local operation.
You could say that. They collect the simple yes-no data from the smart dust. They collect the pre-filtered tracked versus wheeled data from the tactical pucks. They synthesize that massive volume of information locally.
And then what?
And then they beam the consolidated high-value information packet, the confirmed target data, to the battalion headquarters. And they do that using high-bandwidth commercial protocols like satellite communications or long-range Wi-Fi.
So they're the gateway. They link the cheap, ubiquitous commercial mesh on the ground to the classified high-end networks that are higher up the chain of command.
That's their entire purpose, the bridge between the disposable and the permanent.
Okay, now we get to what, for a lot of traditional military planners, is probably the most contentious part of this whole pivot.
The reliance on commercial standards for communication.
Exactly. For decades, proprietary waveforms and customized radios were seen as the only path to battlefield security. MIoT just flips that script entirely.
It relies on the massive R&D investment of the private sector, using everyday protocols like Bluetooth, Thread, and Wi-Fi for low-power mesh networking, plus ultra-wideband, or UWB, for really precise geolocation.
So the immediate, and it is a legitimate question, is how can cheap commercial communication protocols possibly be secure and survivable on a contested battlefield?
And this is where the security architecture is, frankly, genius, because it leverages the same advanced hardware and software protocols that protect your financial data every single time you use a payment app on your mobile phone.
And the source material uses a fantastic, really accessible analogy to explain this technology, the Intuit Dome example.
Home of the LA Clippers. It's the perfect parallel because it illustrates secure location sharing at a massive scale. The system, called Game Face ID, relies heavily on ultra-wideband.
So how does it work?
It's leveraging the basebands in everyone's pockets. Thousands of fans are broadcasting their identity via Bluetooth and UWB beacons. The Dome network then triangulates that signal down to a specific zone, which allows the system to authorize your entry or your purchases without you ever pulling your phone out.
And that UWB technology is incredibly precise.
Centimeter-level accuracy, far beyond what standard GPS alone can do, which, as you can imagine, makes it perfect for pinpointing a target's location on a battlefield.
Okay, but if they're just shouting data over the airwaves using Bluetooth, a protocol that anyone with a laptop can access, why can't an attacker just listen in and spoof an identity or steal data?
That's the million-dollar question. And the answer is a multi-layered cryptography layer, specifically public key infrastructure, or PKI.
So the phone isn't broadcasting raw data.
Not at all. It transmits a randomized, single-use encrypted token. And that token is fundamentally secure because it has been cryptographically signed by the phone's Secure Enclave.
Let's break down the Secure Enclave because this is the absolute linchpin that makes all of MIoT possible. What is it functionally?
Think of the Secure Enclave as a physical, hardware-isolated micro-vault that's built directly into the silicon of the processor.
So it's a separate computer inside your computer.
Essentially, yes. It is physically separated from the main phone processor. It runs its own microoperating system, and it is inaccessible even to the phone's primary OS. This is where the actual, non-extractable private keys are stored. And critically, the hardware itself is designed with secure boot processes and anti-tampering measures.
So the transmission itself is protected by multiple layers of math.
That's a great way to put it, yes. The initial handshake uses something called elliptic curve cryptography, or ECC. This is vital for these low-power sensors because ECC uses much smaller key sizes than traditional encryption.
Which means less work for the processor.
And far less battery drain for that initial negotiation. Once the connection is established, the actual data payload is protected by robust military standard AES-256 encryption.
So if an enemy intercepts the raw Bluetooth packets,
They see nothing, just randomized mathematical noise. They can't clone the identity, they can't steal the keys, and they absolutely cannot read the sensor data.
So the MIoT architecture is just taking this exact commercial security model and applying it directly to the battlefield. And this seems to address the big concern, which is, aren't we just handing the keys to national defense to companies like Google or Apple?
No. We are leveraging their trillion-dollar investment in security R&D, but we are not handing them the keys. The application is that the sensors use cheap commercial basebands to shout, "Target here," over inherently noisy open airwaves like Bluetooth or Thread.
But the authority and the security of that data is managed by something else?
It's managed entirely by a specialized military-loaded secure enclave. It's a physical separation of function.
And the analogy they use is perfect.
It is a secure, government-issued padlock on a cheap, disposable commercial locker.
The sensor is the cheap locker. It does the physical sensing and transmission.
And the Secure Enclave is a small, inexpensive, government-controlled encryption chip. It's a tamper-proof padlock that holds all the cryptographic secrets. So if the enemy captures the sensor, what do they get?
A $50 piece of plastic, a microphone, and a battery.
Exactly. But the crypto keys remain secure within that physically isolated hardware vault. This simple architectural separation is what allows us to use high-volume, highly consumable hardware in the most secure way possible.
Okay, so deploying thousands of sensors solves the asymmetry and the cost problem, but it immediately creates a new and potentially paralyzing problem, the data challenge.
Right. You move from having almost no information to having a deafening cacophony of raw, unprocessed noise. The question then becomes, how do you prevent that data from completely paralyzing human command decisions?
And that is the operational crux of MIoT, isn't it? The hardware is totally useless if the human architecture can't interpret the input in time.
And the solution is to transform the battalion command post into what the paper calls an edge compute node. This is a fundamental change in how the data flows.
This transformation is immediately necessary because of the bandwidth problem. If you have thousands of Tier 2 pucks recording raw acoustic and seismic files, I mean thousands of high-resolution files detailing every passing vehicle, every bird, every footstep.
You just cannot transmit that volume of raw data over a limited satellite link from a contested area.
It's impossible.
It's functionally impossible. The latency and bandwidth limits make it a non-starter. Think of it like trying to stream 4K video over an old dial-up connection, all while you're under enemy electronic attack. It just won't work.
So the edge compute node processes the data locally.
Locally, at the lowest necessary echelon, which is typically the battalion. The battalion vehicles are now housing ruggedized blade servers that are running commercial machine learning and AI algorithms.
Similar to the kind of filtering AI in a smart home speaker or industrial system.
Exactly, similar to the powerful AI used for anomaly detection in factories.
And these systems are trained to synthesize specific inputs. So what does that synthesis look like in practice on the ground?
The AI algorithms filter all the noise, and then they correlate discrete sensor events from across the entire mesh. For example, the AI identifies that sensor A heard a specific diesel engine frequency, plus sensor B felt a correlated, heavy 40-ton vibration pattern at a specific time, plus sensor C measured a high magnetic signature. The immediate AI-verified output is the confirmed conclusion. T-90 tank confirmed, moving northwest at 20 kilometers per hour, location, grid XY.
So the human commander never receives the raw data. They just get the analyzed, verified conclusion, the platinum score.
Correct. The battalion absorbs all the complexity, all the raw audio, all the processing, and they export only clarity. The verified, actionable target packet goes up to the brigade or higher headquarters.
This dramatically reduces the necessary bandwidth and, I assume, decision-making latency.
Critically, a lieutenant on the ground receives a verified target packet, not a request to, listen to an audio file and try to decide what it means.
And this federated edge-based processing approach also provides a really significant and maybe unheralded solution to a perennial problem in alliance warfare.
The NATO interoperability crisis. This is a vital geopolitical advantage that comes out of this.
Historically, allied data sharing has been so hampered by classification levels.
It's been a nightmare. If, say, a Polish sensor detected a target and a U.S. unit needed that data for a fire mission, the information had to go up the chain to a highly classified U.S. headquarters.
Be scrubbed, sanitized.
And only then could it be sent down to the partner nation. This bureaucratic delay often introduced lethal latency. People die in those seconds and minutes.
But because MIoT starts with cheap, commercially available hardware and protocols, the base data is essentially unclassified.
That's the key, because the underlying transport data starts as unclassified open standards. We're talking simple things like JSON packets or MQTT messages. We can implement sophisticated, granular, federated access control right at the edge.
At a Tier 3 node.
Exactly. We don't need the headquarters middleman anymore. We can grant a partner nation immediate access to a specific geographically relevant mesh network, say sector alpha mesh, using a crypto key. And we can do it before that data ever touches a high-side classified network.
That allows for true tactical speed and, I guess, trust.
It enables immediate bidirectional information flow. A U.S. fire support element can subscribe to a polar sensor mesh, and vice versa, and instantly see those platinum scores. The key here is not just that the data is cheap, it's that the format, JSON or MQTT, is inherently simple and fast to share across diverse national systems.
So a multinational force can operate off a single, unified, real-time operating picture.
Without waiting for bureaucratic clearance from some headquarters 1,000 miles away, the security is mathematical, handled by the Secure Enclave, not administrative.
Now, this MIoT concept isn't limited to just passive intelligence gathering. It completely transforms active combat applications, too, particularly in countermobility.
This is where we get the concept of the intelligent obstacle, or smart minefields. This application fully leverages the thread networking protocol, which is a core piece of that commercial standard stack we've been talking about.
And thread is crucial here because of its self-healing mesh topology.
Right. A traditional minefield is static, it's non-communicative, and it's just as dangerous to friendos as it is to the enemy. By integrating this Internet of Things architecture, we turn those individual mines into secure networked nodes.
Which gives the commander assured remote control.
It turns the static obstacle into a maneuverable one.
Okay, so why thread specifically? Why not use standard Bluetooth mesh or just Wi-Fi?
Thread is optimized specifically for low-power, self-forming, and self-healing networks. That's exactly what a minefield needs. Bluetooth mesh relies on a central gateway, which is a single point of failure. You take that out, the network is dead.
And Wi-Fi is just too power hungry.
Far too power-hungry for devices that need to sit dormant for months. Thread allows every single device, every mine, to act as a potential routing point. So if one mine is neutralized, the network instantly and automatically reroutes the command signal around that gap. It maintains continuous connectivity and control over the whole field.
And Thread defines 3 specific roles for these nodes in the minefield.
It does. First, you have the border routers. These are the critical gateways. They bridge the minefield's mesh network to the battalion's external command network, often via satellite. They ensure the field is online and can receive global commands like ARM or SAFE.
Okay, and then second, you have the standard routers.
These are the heavy lifters of the network. They actively repeat the signal and maintain the network topology. Their health is key to the survivability of the mesh. They build in that redundancy, so if heavy fire takes out a section of the field, the communications flow continues seamlessly.
And finally, the vast majority of the nodes are the end devices.
These are the sleepers, the actual explosive components. They use Thread's deep, low-power function, so they stay in a minimal energy state to preserve battery life for months, maybe even years. They only wake up instantly when they get a concerned sensory trigger or when they're pinged directly by a router requesting a status update.
The operational advantage for maneuverability here is just enormous, especially when you think about reducing that factory-to-fight logistics burden that comes with static obstacles.
Absolutely. Because the commander has that assured remote control, they can remotely toggle the field to safe or off instantly. They can allow friendly counterattacks, recovery vehicles, even civilian movements to pass through safely.
And they can pick them up and move them.
They can recover and redeploy the assets somewhere else if the operational situation changes. The obstacle itself becomes a fluid, adaptable component of the whole maneuver plan.
And the technology also addresses major ethical and legal requirements. It supports the intent of things like the Ottawa Convention, particularly around discrimination and persistence.
This is a profound ethical leap forward. In terms of discrimination, a legacy anti-vehicle mine relies on a single pressure plate or maybe a magnetic sensor. It's very prone to error. A smart mine fuses data from multiple low-cost sensors, seismic, acoustic, magnetic, all linked in that secure mesh.
So it achieves that high-confidence platinum score we talked about.
Which means it can filter out non-targets. It can fuse the data to distinguish definitively between a heavy 40-ton tank, which is a valid military target, and a 15-ton civilian school bus, or even a local farmer's tractor. The system will refuse detonation for the latter. That ensures better adherence to the laws of armed conflict than any previous generation of landmine.
And what about persistence? It tackles that terrible post-conflict threat of unexploded ordnance that endangers civilians for decades.
Yes. The intelligent field requires an active heartbeat signal from the command network to stay armed. If the conflict ends and the control signal is manually turned off, or if the internal batteries of the routers just die over time, the entire field automatically neutralizes itself. It becomes inert.
Which prevents those post-conflict civilian casualties.
It does. And furthermore, by integrating Blue Force tracking signatures into the mesh's identification algorithms, you virtually eliminate the risk of fratricide during complex friendly maneuver operations.
All of this operational and ethical advantage really culminates in the fiscal proof. This is the necessary conclusion to this deep dive. Let's look at the cost per kill comparison case study to really hammer home the economic imperative.
All right, we have 2 options for taking out a single enemy T-90 tank. First, the legacy method.
This relies on high-value, high-risk assets.
You launch an MQ-1C Gray Eagle drone that costs $21 million. You fire a $150,000 Hellfire missile, and the drone has to linger over the target area to use its proprietary optics, which immediately risks that $21 million airframe to enemy air defense or electronic warfare.
So the total financial exposure, the loss potential in that single engagement is huge.
It's over $21 million.
Okay, now compare that risk to the MIoT method.
The MIoT method uses the disposable network and ground assets. So the investment is a network-attached launcher container, about $1 million. It fires a ground-launched effect munition, about $50,000. And crucially, the sensor input comes from a mesh of 20 cheap, disposable smart pucks.
At $100 each.
For a total of $2,000 for the entire sensor network.
And the process is simple. The cheap mesh triangulates the tank's position, the edge compute AI verifies the platinum score, and that data cues the launcher, which is miles away, safe.
Correct. The ground-launched effect can be fired safely from a low-risk, secure position, often far behind the front line. The critical difference is that the maximum financial exposure of the assets at risk is the $2,000 sensor mesh plus the $50,000 munition.
So the total financial exposure of high-value assets is negligible, while the total cost of the strike itself is only about $1,052,000.
That's staggering.
That comparison is just, wow. Even factoring in the cost of the launcher, the MIoT method is roughly 20 times more cost-effective just in terms of risk exposure.
Yeah.
And it preserves those expensive platforms.
And that's the key, preservation. You use inexpensive disposable systems for the routine attrition missions, which is the bulk of the fighting, and you thereby preserve your $21 million Gray Eagle, your golden arrow, for the genuinely high-priority asymmetric tasks,
Like hunting critical command nodes or high-value radar installations.
where its sophisticated capabilities are truly indispensable. We move from being economically vulnerable to restoring fiscal sanity to the conflict. The numbers, they just prove the immediate strategic advantage of disposability.
But just quickly, to address a potential risk here, what if the enemy just overwhelms the sensor mesh with thousands of their own cheap drones? How does that affect the system? Isn't the AI just bottlenecked at that edge compute node?
That's a great question, and it's why volume is the first principle of this whole thing. If the enemy throws 1,000 cheap drones at us, we fully expect the mesh to fail in parts. But because the mesh is self-healing, it continues to provide persistent, if degraded, coverage. But more importantly, the AI at the edge compute node is designed to filter noise. 1,000 cheap drones generating acoustic signals simply provides the AI with more data points for correlation. The AI isn't overwhelmed by volume. It's designed to thrive in it. It's built to isolate the meaningful signals from all that sensory chaos. The bottleneck is managed by distributing the compute power down to the battalion level.
The final, and I think most crucial piece of this whole puzzle is acquisition and sustainment. If we're going to adopt a philosophy of disposability and 12 to 18-month commercial refresh cycles, we absolutely cannot stick to the decades-long procurement cycle that trapped us in this mess in the first place.
You can't. We need velocity.
Eh.
What the paper terms the Amazon Prime model of volume and efficiency,
Gosh.
especially given the logistics volume that's required here.
So implementing MIoT at scale requires abandoning that traditional ownership model entirely.
It does. Since the velocity of the commercial market makes buying something and storing it for decades obsolete, we have to look to the successful enterprise IT model, specifically Option A device as a service, or leasing.
So instead of the Army buying 10,000 sensors and putting them into a climate-controlled warehouse for 40 years,
The Army just contracts for sensor availability.
Yeah.
Or data provisioning.
the vendor provides the current generation of technology on demand.
Right. And critically, every 12 to 18 months, the vendor is contractually obligated to swap out the entire inventory for the newest commercial models, the ones with better battery life, faster processors, enhanced features, whatever the global market is driven.
So the system fundamentally avoids the obsolescence trap automatically.
The cost of upgrading is just built into the monthly service contract. The military is always fielding the latest, commercially optimized technology. It's a game changer.
And this leasing model, it also solves a crucial logistical and environmental hazard that comes with disposability, the problem of all those used lithium batteries.
That's the recycling loop problem. If the military is operating under the fire and forget philosophy, leaving thousands of lithium battery-powered sensors all over training areas like Fort Irwin or Hohenfels, you create a massive, complex environmental disposal hazard.
But under the device as a service model.
The vendor is the owner of the assets. They are highly incentivized to recover the materials and handle the specialized end-of-life disposal of those batteries. They manage the entire recycling loop, which is both financially efficient for them and environmentally responsible for the user.
Okay, but then there's option B, the hybrid model. This offers an alternative, maybe for agencies that might be hesitant to fully outsource everything.
The hybrid model proposes that the Army owns the backbone, the critical, high-value, long-term assets like the Tier 3 intelligent nodes, the secure servers, and the central command gateways.
But the cheap stuff.
But the Tier 1 smart dust and the Tier 2 tactical tanks are treated strictly as consumable ammunition. They're bought in bulk millions of units at a time from commercial partners using immediate rapid procurement cycles. This balances necessary government control over the central, classified network with the high-volume disposability you need at the edge. It's a compromise built on recognizing that sensing has to be a consumable resource. So, to summarize the entire argument here, the key to restoring asymmetric advantage is fundamentally economic. We must abandon the mentality of treating our sensors as if they're family heirlooms
As expensive, irreplaceable capital assets.
and start treating them as digital ammunition, consumable and disposable.
By embracing this philosophy of MIoT volume, commercial velocity, and mathematical security, we stop expending $2 million missiles on $500 drones.
We reclaim our fiscal ballistics. We ensure we are spending $2,000 of disposable resources to cue a lethal kill on a $4 million enemy tank. This is the only scalable path forward. It's the only way to reclaim the strategic advantage and maintain force projection without fiscally bankrupting our defense budget against a peer threat.
And the logistics, volume, and velocity that you need to defeat a peer adversary, it just can't be managed by traditional, manual, paper-based processes.
No, it requires the industrial agility of an Amazon Prime model. By adopting MIoT, we ensure the battlefield is transparent to us, allowing for rapid, distributed, and cost-effective decision-making.
The white paper leaves us with this powerful concluding statement, which I think truly resonates with the core problem of information parity. It says, the transparent battlefield is a reality. The only question is whether it will be transparent to us or only to our enemies.
We have to choose to see, and to see cheaply and effectively.
And that leaves us with a final provocative thought for you to consider. If commercial agility and speed become the dominant military advantage, and we're relying on rapid refresh cycles and leasing models for our forward-deployed sensors, does the traditional definition of a classified defense contractor need to be fundamentally redefined?
And what does it mean for national security when the best available tamper-proof encryption, the Secure Enclave, is housed inside a consumer-grade processor chip that was designed primarily for your mobile phone? The very nature of military advantage may now reside entirely within the Silicon Valley supply chain.